Hi again, guys. This is 6.4 example 4, page 341 in your textbook. So this is a force vectors example. Tension is a force. And I'm going to be doing it the way it's done in the textbook in this video. And then tomorrow in our live class, I'm going to be doing it with vector components. So I wanted to show you two ways of doing the same question with two different techniques. Okay, so I've drawn out the diagram here. We've got a stoplight that's hanging with a weight of 2,500 newtons downward, and then it's being held up by two cables. It says, now, in the textbook example, they call them tension 1 and tension 2, the tensions in the cables. However, since these angles, the angles that they make with the horizontal are the same, and since they're both holding up one weight, and since those angles are the same, we know that those two cables are going to share the weight of the stoplight equally. Therefore, the tensions are equal, and so I have just called them T. I've just called them both T because they're the same. Okay, now, in order to solve this problem, we need to do a few things. One, we need to recognize that this 2,500 Newton weight downwards is actually the equilibrant of the tension vectors. And the reason it's the equilibrant is because it is balancing out the addition of those two vectors to keep the stoplight stationary. So the stoplight is not going anywhere, hopefully. It's just staying suspended in the air. And the only way that could be possible is if the forces acting on the stoplight are balanced. And so therefore, this equilibrant, the weight of the stoplight is the equilibrant. And what we actually need to find is the opposite of that vector, the resultant of the two tension vectors, or we need to use that to find the tensions because the tensions are unknown here. We know that the resultant must be equal to the equilibrant because that's always the case. So we actually do know at this point that this resultant vector is 2,500 newtons in an upward direction opposite to the direction of the equilibrant vector, which is the weight of the stoplight. All right, so I have taken my tension on the right here and slid it up to be tip to tail with the other tension. I could have moved the other one, doesn't really matter which one you move, they just need to be tip to tail. And so they're positioned tip to tail now with the resultant going from the tail of the first to the tip of the last. And this angle in here, this 10 degrees, we know that that's 10 degrees because we were told that this is 10 degrees. And we have a Z pattern here, 1, 2, 3, where there's a horizontal at the tail of this tension vector. So this would also be 10 degrees. And so if I slide that vector up to the tip of the other tension vector, the angle to the horizontal will still be 10 degrees. So that's why this one here is still 10 degrees. Which means that my entire angle in the triangle here is 20 degrees. Now, since the tensions are equal, I know that this is an isosceles triangle, which tells me that these two angles, 1 and 2 down here, must be equal. And 180 minus 20 is 160, and half of that is 80, so therefore I know that these two angles here are 80 degrees. Now what I want to find is the tension in the wires, and so I need to solve for T. Now I have a triangle where I know 3 of the angles and 1 of the sides, and so I should be able to use sine law to find the unknown side T, the magnitude of T. So I'll start with magnitude of T, and that needs to be over the sine of the angle across from it, either one, they're both 80 degrees, doesn't matter. And that has to be equal to a magnitude that I know, which is 2500 newtons, over the sine of the angle across from it, which is 20 degrees in that triangle. Okay, if you do your math and isolate the magnitude of t, then you should come out with an approximate answer of 7198 newtons, or if you want to round it up, 7200 newtons, as they did in the textbook, but it doesn't really matter to me whether you do or not. And then we just need to look at the direction of that vector. So the direction is actually already given. It's 10 degrees below the horizontal. It's already given for both the tension vectors. So tension is approximately equal to 7198 newtons at 10 degrees below the horizontal.